name is Anna Minihart, and I am your moderator for today's talk. I'm here with our guest, Dr. Enhao Gong. He's an electrical engineering PhD with a focus on AI medical imaging out of Stanford University. In today's discussion, Dr. Gong is going to talk to us about deep learning and how it enables at least 100-fold dose reduction for PET imaging. Everybody will be muted during the discussion. However, if you do have a question that comes to mind, go ahead and click to your right the drop-down screen that says questions and simply type your question in and click on send. We'll address all questions during the live Q&A session after our talk. Dr. Gong, how are you today?
Good.
Good, great to hear. Before we get started, what do you want to make sure that everyone can take away from today's talk?
Yeah, I think there are several points we want to address. First, we want to talk about what is low-dose PET and why it is valuable. And second, we want to introduce how deep learning can provide more accurate and efficient solutions than other methods. And last, we want to talk about how this technology can be applied for oncology applications and for better detection for Alzheimer's diseases.
Dr. Gong, though most of our viewers are probably already familiar, can you give us a quick refresher on PET and more specifically why we want low-dose PET and why it's so hard to achieve?
Sure. So PET, the full name is positron emission tomography, and it is a cutting-edge medical imaging technology special for nuclear medicine. And it's also called a type of molecular imaging modality because it shows not only the structure, the tissue contrast, but also the molecular activation inside the brain or body. So it can map the function, which is very important. And it is also used as a multimodality imaging because it will compare with MR and CT to give higher resolution. And during the PET exam, usually the patient is injected a radiotracer for imaging and wait for time for the tracer to get uptake and to imaging the distribution of the tracer. And the tracer contribute to the image quality, but it also increases the risk of our radiation exposures. And also it increases the cost of the exam because a tracer may cost a couple $100 to a couple $1,000. So there's a clear trade-off between dosage, safety, cost, and benefit. And that's why we want to enable low-dose PET imaging.
So can you summarize your research methods used to achieve this low-dose PET?
Okay, there are several components in this method. First, we were collecting big data sets to simulate the dose reduction. From the rawly small data set, we can undersample it to simulate 100 to 200-fold dose reduction as if you inject 99% less injected tracer or 100 times faster acquisition. In this way, we have paired data sets. Secondly, we're using the multimodality information. So we use not only the PET signal, but also more information from the structure imaging, such as MR. So that's the advantage of using simultaneous PET and MR. This provides more information and better tissue contrast that can lead to enhanced image quality. Third, we train the deep learning model, which is also accelerated using GPU. So the model we use is so-called a deep residual encoder and decoder network, which have several features, including improved image quality and the usage of multi-scale information. And we further evaluated an in vivo dataset. So here is an example of a paired dataset. So on the left-hand side is a low-dose PET. So it shows the simulation result from a 0.5% low dose, which is as if we reduce 99.5% of the radiation. And we can see the image quality is poor because it has so few information we can use. And on the right-hand side, it shows the standard dose ground truth. In this case, it's FDG PET as oncology cases. So in this way, we try to train the deep learning for nonlinear reconstruction to map from the left to the right. And also, as I mentioned, we use multimodality information, also demonstrated in this image. On the left-hand side is the 0.5% low dose, and in the middle, we show 3 contrasts from MR. So basically, we're using the 3D multi-contrast MR to provide much better resolution information. And both of the PET and the MR is used as input to map to the image in the right hand. So this image shows the network structure we were using. It's a little bit crowded, but what you want to understand is deep learning here can be considered as layers of filters. So there are several layers of filters concatenate each other, and we get a high quality image at the end. And what the filter does is specific filtering, which is trained with a numbers of examples. And here we also show a lot of connections called concatenation connection and residual connection. What it does is to bring information from different resolution and different scale to improve the result.
So how are others achieving this, and how is your approach different or better?
Yeah, there are several other methods people have tried. First, of course, we can further improve the hardware by using better but more expensive sensors. However, there are limitations about how much it can improve, and of course, it's higher cost. Second, people try to use conventional denoising algorithm for this. There are commonly used denoising algorithms such as non-local mean method and BM3D. It is commonly used for image denoising, but it also provides only limited improvement, and the processing can be very slow. It can take minutes to hours to process a single image, so it's not clinically applicable. People also propose to using deep learning methods or other AI algorithm, but they only shows limited improvement and only on simulation datasets. So here, what our algorithm does is trying to improve further than previous methods, but also achieve higher speed and higher performance. So we did some quantitative comparison and shows our algorithm is actually significantly better than other algorithms, and also comparably applying the proposed methods is way more time efficient. And further improvement using optimized deep learning and GPU accelerated framework can also further improve the speed. So here shows how our method is better. First, it's more accurate. Here shows the quantitative metrics demonstrating the proposed method is significantly better than previous method. It shows over 8 dB improvement than low-dose PET and 4 dB improvement than other methods. Also, in this graph, it shows it actually more efficient. Applying the proposed method is time efficient, and we can see more improvement with further hardware and software development.
Okay, so let's show our viewers some actual image results. Can you walk us through these?
So here, this is an example of a glioma case. It's an oncology application. So here on the left-hand side, we show 6 comparisons of the brain image. The upper left is a reference ground truth standard dose PET. And the second one shows low dose PET is really have poor quality, high noise, so it cannot be used for clinics. And we show the comparison of different methods, and it demonstrates our proposed methods significantly better than other methods. It shows better structures. And on the right-hand side, we show a zoom-in image of the blue box on the left. So here shows basically where the lesion is. And on the right-hand side, we compare the details and also find the proposed method is better. It's better outline the lesions and can use for clinical applications.
So others claim 2 to 4 lower dose. How is it that you can achieve 100 times lower dose? What's the secret?
Yes, we do have some special design of the algorithm. The most important feature is we are using the information from MR, which provide good tissue contrast and high resolution. So here shows an example. It's a comparison of the ground truth standard dose PET and the low dose PET and the model pure deep learning without using MR and the model we propose using both PET and MR. This clearly shows by combining deep learning and combining MR information to the PET information, it can generate much better quality. It shows better contrast, better structure, and better resolution.
So you show this can be used for oncology applications in the body. What other applications can you use ultradose or deep learning for?
Yes, there are a lot of potential applications. We have shown some examples for oncology applications. Here we show it can also be used for the detection of Alzheimer's disease. So for Alzheimer's disease, which is a chronic progressive symptom, so here shows an example for the ultra-low dose amyloid PET. So the leftmost is a T1 MR, is used for structural imaging, And the second is full dose PET, amyloid PET. It's the gold standard for diagnosis. And on the right-hand side is starting with the low dose PET. You can see the quality is so poor, so you cannot use it for clinical diagnosis. And with PET-only model, without using MR, you get a little bit better. And with using MR, you can actually get almost the same as a full dose PET. So therefore, you can enable ultra-low dose amyloid PET.
So Dr. Gong, what's next in your research plans? Can you give us a sneak peek?
Sure. We are keep working on clinical evaluation on larger cohort to see how these methods, this technology can be generalized. And we're also exploring different radiotracers and different applications. For example, we have shown it works on FDG PET and on amyloid PET. And we are keep exploring are there any other applications. Also, we are developing streamlined pre-processing pipeline. So this can lead to more efficient and scalable solution. So we can make the product to be more stable and higher performance. And last, we are improving the technology for more applications. We have shown it works on oncology and neurology and more. And we are also exploring a zero-dose PET applications so we can completely using MR for molecular activation map.
At this time, we're going to cut the video and open up the floor for our viewers. So don't be shy, we want to hear from you. We'll start with the questions that have already been submitted. If you haven't already, go ahead, submit your questions by following the instructions on your screen. We'll get started in just a few seconds. All right, everyone, the questions are coming in. So I'm going to read these kind of as a first come, first serve. Feel free to keep submitting. I see some additional questions coming in. First one is this available right now?
So I have to say this talk or this like a presentation we have or the interview we have is more focused on trying to introduce recent academic research we conducted. And so we shows how it's applied in oncology cases and potential in amyloid PET from Alzheimer's disease. So, and we at Sun Medical definitely trying to work hard to make it available for clinics. And we recently got FDA approval for our first product called CytoPET, trying to do this, and we got cleared for do denoise image and so enhance image quality. And we work with our like hospital partner try to make this into clinic usage. And our hospital partners demonstrate it can help them enable faster scans. Some of them shows a 4 times faster scans directly from the products. So that's is what available, but there are a lot more potentials from the technology. We can further push better scans quality.
Great. Second question is, does this mean we do not have to further invest in better hardware for PET scanners as algorithms can do everything?
Yeah, I think there's some discussion about, say, the software is eating the world and AI is eating the software. But I think definitely everything is compatible in a way to everything has to be co-developed. So first, all this algorithm is considered as post-processing. So it's also we designed to be compatible for all the hardwares. So in this way, definitely better hardware design, better sensor for PET leads to more improved performance. So and build on top of it, if we add more algorithm, we can also further improve the image quality and for better image experience. And recently, there's an editorial published by another researcher and published in Radiology journal. And actually, he has did a really good survey on recent development in both hardware side and software side. And by combining the best hardware development and best software AI development, there are potential to even push to say 10,000 times dose reduction. But it's something is the potential of the combination of hardware and software. So definitely there are a lot more development needed in both hardware and software side.
Great. Okay, third question. I'm a little unclear how you were able to collect all of this data or simulate low-dose PET accurately. Could you elaborate on this?
Yeah, I think there is already been industry or academic standard. We also refer to several other papers already published. So in this way, because PET have some unique way it is collected, and all this data is stored in the list mode data. And if we able to read the list mode data, it's basically a collection of all the events collected by the sensors. And so for the more realistic simulation for the low dose, people usually do is randomly or uniformly undersample it and try to as if there are only certain percent of the events collected, which means as if there's a certain event of activations going on. And so that's how in academic settings and industry doing the simulations. So I think a lot of benchmark paper published in this way. And we can also doing this by take the first or second or different time point and consider as a frame. And so that's how people are doing dynamic PET, or people can simulate the faster PET. So that's how we do the simulation. Is pretty academic standard.
Great. Next question. Is this actually low-dose PET? It seems like PET is not needed at all, or why is it needed?
Oh, so definitely is. So basically, this is we leverage the information in not only in the PET but in other modalities. So for example, the PET CT, there are information in the CT which is very high definition, high resolution, high quality, and can actually be leveraged to improve the quality of the PET, where the PET actually captures a molecular activation, the function that is very important for oncology detection, staging, or neural disease detection and diagnosis. And similarly, we shows for PET MR, maybe even better because in MR first is radiation free, but also there in theory there are infinite possible way you can collect MR to generate infinite number of contrast. So the soft tissue contrast in MR has a lot of information to characterize different tissue type, and in this way, this kind of segmentation or this kind of tissue combination can also be, this information can also be used for the image enhancement of the PET. So all the information from, we take information from CT or MR, which is more anatomical, to put this information into PET, and by using deep learning, we train an end-to-end model, try to leverage all the possible information. So both in the original low quality PET, even though it's low quality, but there are a lot of useful or the necessary information for the functions, and also the information from the anatomical imaging. So by combining this twofold information is how we can really push the limitation of like a faster scan or low-dose scan.
Next question. Do you think it is necessary to utilize deep learning or machine learning for other bioimaging methodologies?
Oh, I think definitely this is a trend, or not only a trend, but already is being developed, have developed and being developed and keep developing. So I think at Stanford, we develop a lot of algorithm on both MR and PET and CT. Basically for MR, here we talk more on the image workflow, image enhancement than the diagnosis side. So for MR, it's like we can enable faster scans or enable better reconstructions. And for CT, there are low dose. There are a lot of paper publishing for CT low dose. And for PET, we shows it can further improve, we call ultra low dose, or try to push the extreme case to make the PET more safer and accessible. And also recently, I think there are very high profile paper publishing, say for microscopy, like you can take, using deep learning, you can get more information from a low quality microscopy image to transform into certain type of image that can be used for different detections. So I think a lot of biomedical imaging applications can leverage this, and I see a lot already going on in academic.
Okay. Next question. Is the algorithm applied on the DICOM level or as a part of the image reconstruction?
Yeah, I think there are opportunity in both pre-DICOM and post-DICOM phase. So, and I think there are a lot more possibility if we can do it before DICOM, because definitely in the DICOM conversion, like basically the reconstruction, the step compress a lot of information into the image. So there are some information is missing. So if we can do in deep learning pre-DICOM, and we have some publication on this, and also there are other groups also trying to do that in not only in maybe PET or MR or CTs. Basically, it can be a new type of reconstruction algorithm and shows better results than conventional iterative fixed model-based computer sensing method. So that's definitely a lot like improvement can be done pre-DICOM and also post-DICOM. So here I think this like we in the interview we talk about this technology is mostly post-DICOM because we also wanted to generalize for different scanners and even different tracers, different body type applications. So we try to make sure it's generalized. So DICOM is definitely a format that's very standard, everyone use. So it can give us the like standardized way to process image. So just in short, this interview we talk more of this technology is post-DICOM, but there are a lot of research we're doing pre-DICOM as well.
Great. Next question, 1/100th FDG patient dose is pretty small. Can Newcomb pharmacists prepare or calibrate such a small dose without issue?
I think there's definitely questions we are also considering, and we trying to talk with pharmaceutical companies, and I think they're learning this is opportunities for them to give to have new product with better safety profile as well. But definitely, I'm not completely sure, to be honest, for how they can really manufacture 100 dose. But one thing is this enable a lot of more extended usage. So for example, when there are a lot of cases in clinics, people shows up late. It's like if it shows up one like half-life, that's already got quite a low dose. So that's definitely not only you can, there are a lot of ways to use the technology. You can usually use it with low injection or low density injection, or use it for faster scan, or use it for some cases people shows up late, or for cases that just the high full dose scan is not available. So I think this coverage a lot of applications, and the question is what's the best way to use it, and we are exploring, and we are working with partners to further exploring that.
Great. Please explain how low dose PET was simulated using full dose data. What is subsampling?
I think this is already somewhat answered in previous questions. So basically, because PET has the least mode, it's basically raw events collected, and we can subsample means you just say ignore randomly some events. So in this way, you simulate as if there are lower dose or lower event generated. So I think this academic and industry standard to simulate it.
Next question, at test time, do you need both an MR and PET scan or just a PET scan?
I think that so for if this scanner is PET MR, definitely using both PET and MR is the best. And even we should also use PET and AC map, definitely give better results. But if this is PET CT, or also if you want to apply the same algorithm in both PET CT or PET and PET MR, or this is a PET only scanner, which is also like used in some applications. So the algorithm can just take only the information from PET and to get the low dose, and which is not as good as you leverage all the information, but it's actually still have deliver a good quality.
I think this is a similar question. This FDG dose reduction is for PET MR only, or will the algorithm work for PET CT?
Yeah, it's similar to similar
Okay.
image, including what I just answered. Okay. So similar idea can be used in PET CT. But here we talk about PET MR because this also provided extended usage because MR side there's no radiation. So if you further reduce the PET, you can really give a really low dose and safer and accessible exam. But for clinics, definitely a lot more PET exam is on PET CT scanner. So there are both research we're doing and the products we like development at Sun Medical is focused like on PET CT
and PET MR. So it's generalizable.
Okay. How do you register so poor quality PET image with MR image and CT image?
So I think so in academic setting we can use a lot of fancy co-restriction, which is like can be time consuming. So we do that. It's like both consider rigid and non-rigid motions. But in academic or clinical settings, usually we're trying to not so much push the co-restriction. But definitely the trade-off is without too complicated co-restriction, you may not get the optimal best quality, but you can still improve it because there are definitely something related in the MR you get it. And in the usually DICOM, there are headers talking about what's the field of view, what's the different resolution. So it's already very easy to align them together. So it's not that big deal. But there are definitely a lot of motions for some, especially for patient cases. Because if PET scan is very long, it's 20, 30 minutes, some patients cannot hold still in the scanner. So there might be motions. So that's definitely introduce some difficulties for this type of multi-control algorithm. But on the other side, if we can do in low count, or we can enable faster scans, basically we can also reduce some potential motion issues. If you cannot hold still for 20 minutes, maybe you can hold still for 50 minutes. So definitely in the different way we solve this motion problem. Yeah.
All right, next question. Do you think your algorithm could be adopted to other nuke med modalities such as cardiac? If you can reduce isotope dose by only 1 order of magnitude, let alone 2, you solve a dire TC and Mo shortage problems that never seem to go away.
Yeah, we are trying to work on that and also exploring different opportunities, and happy to learn more about this. I'm not a cardiac expert, but we're talking with cardiologists and definitely find their applications, and we are trying to develop explore that. So first, in this PET MR, PET CT settings, they are also cover, say, the bed will include a cardiac part of the body. So usually we take whole body PET exam, and so there are a cardiac part, and we shows actually the algorithm generalized on cardiac because we train not only on brain but also train on and evaluate on different body parts. So it's generalized for different anatomy, including cardiac. But definitely we haven't explored different type of cardiac tracer yet. So there are definitely a lot of opportunities there.
Got it. All right, next question. Do you guys use any computer vision? I'm not entirely sure if you utilized any toolboxes or packages such as TensorFlow or MATLAB, deep learning, or computer vision toolboxes.
Yeah, so usually, so basically it's a deep learning. It's a deep learning applied in image processing. You can consider it a subset for computer vision. And so we use deep learning like TensorFlow, like the infrastructure framework that's open source, and I think most people use either TensorFlow, Keras, or PyTorch, different framework. And so this enable good, easier algorithm development, evaluation, and put it into product. So yeah, so yes, we are using the framework and specifically using TensorFlow.
Great. It looks like we have a few more questions, a couple more minutes if you guys want to stay on the line. Next question is, how is the algorithm different to iterative reconstruction, such as compressed sensing-based reconstruction?
Yes, so compressed sensing for medical imaging, maybe for MR or for PET, for CT, has been developed for maybe a little over a decade. So, and one of the early research in MR application is also published in our lab. And this takes 10 years for this really goes to clinics. And one of the major issues is compressed sensing based on more simplified signal model. So basically you have predefined signal model, say the image has to be sparse or minimize certain norm in a certain transform. So this limited its results because usually the image looks like just different than what as if you will collect a full dose scan or full scan like MR or CT or PET or like other image modality. And so definitely there's a new trend going on. So basically deep learning here it's not replacing radiologists. We are replacing or improving algorithm. So it's if you can also consider it's still a compressed sensing algorithm because you use less data sets but get better quality by leverage the algorithm. But differently it's different in several ways. First, it's a data-driven model, so it's not imposing certain simplified model. So it's usually you can get not only accurate but also realistic image like output. And also usually is significantly more accurate quantitatively than conventional methods because you leverage a kind of complicated model and there are a lot of parameters you can optimize it to get good quality. And also it's complementary here because in the interview we discussed and also when the product we try to first go to market is post-DICOM. It's DICOM based, and we wanted to generalize for different applications and different scanners. So and also different scanner built in has some common sensing algorithm already going on. So it's complementary with this conventional methods. And I think another last but not least, like advanced is this type of deep learning algorithm for imaging enhancement is usually way faster because is just a simplified model, and also is because of development in all these infrastructures, like as I mentioned in previous question, that using TensorFlow, and we leverage GPU, CPU better using like different toolbox from NVIDIA, Intel. Although a lot of going on in this entire industry and enable us to deliver fast processing and enable even real-time applications.
All right, let's keep going. We only have a couple more questions here. Thanks for staying on the line, everyone. You've spoken a little bit to this, but we'll see if you want to add anything additional. Deep learning usually is a black box. How do you make sure your output provides consistent diagnostic information?
Yeah, I think it's a very important question because we not only want to generate like fancy looking image, because we know deep learning can generate like very realistic faces recently, like high resolution realistic face. So there are a lot of capacity in these models, but we actually for radiology application, we want it to be accurate. We wanted to have the right diagnosis information that help clinician make decisions. So there are a lot of clinical related evaluations has been done both for the research and shows in the papers and shows in our research studies, and also keep going on within both Stanford and Sun Medical. So first of all, say for the oncology, say the like GBM applications, we for the low dose PET like paper in this, which shows we also doing tumor segmentation because that's the key task like valuable in clinics, and we shows this algorithm give a consistent results. And also for like amyloid, there are positive and amyloid PET, there are positive and negative readings, which is directly related to like Alzheimer's disease diagnosis and detection. And we show basically with this algorithm, you can get like consistent accuracy if you ask the radiologist to review the image. And also for different applications, we also quantify the quantitative SUV value for different lesion types. And so there are a lot of ways to further improve that, to make it more quantitative. I think the entire field is also not only on PET, but also on MR, other image modality, people trying to do quantitative analysis. So there are definitely like a lot of quantitative tools or evaluation methods we can use to make sure the result is accurate enough.
Great. We actually have a question from a third-year undergrad who wants to know if you have any advice on making a transition into working into in this intersection of deep learning and medicine. He's unclear of kind of how to enter the space. Do you have any advice on?
Yeah, I think I'm very lucky. Like my both co-founder and like my research collaborator and advisor there. I think they're because at Stanford, we have a lot of collaboration between the WE and the radiology. So there are a lot of joint projects, and I'm very lucky to be involved in this project. I work with Dr. Greg Zahachek and Dr. John Pauly and a lot of other faculty at Stanford. So basically, I think you can try to reach out to clinician or clinical researcher to ask what's the questions, what's the pinpoint in both the academic side and also maybe clinical side. And so basically we want to find the needs first and then to see whether it is a good application for deep learning. And what is good application for deep learning, I think, is first there has to be some reference data sets, like a pair data sets, and basically it's a mapping problem from image to image or image to labeling, and also deep learning basically try to leverage enough data set, try to learn this mapping, and try to solve different clinical questions. So I think to find the right question or right problem to working on is more important than just use deep learning. So I think maybe talk to people in clinical side to see where is the pinpoint, where is the questions they try to solve.
Well, it looks like that's our last question for the day. Thank you to Dr. Gong for being here. We really appreciate you sharing your insights and your research with us. We're going to go ahead and wrap up today's webinar. You'll be able to see a recorded version on our YouTube channel, Subtle Medical. You can just put that in the search bar and should pull up our Subtle Insights webinar series. These webinars are really meant to highlight things that our viewers want to see and want to learn about. So if you have any ideas of what you want to hear about next or someone you want to hear from next, be sure to ping us. Send us any ideas you have, and we'll definitely take that into account. We'll try to do these again, every month or so. So stay tuned for the next one, and we'll see you next time.